Start recording. There we go. And page 101. Okay, so here we are with our titration curve of a weak base with a strong acid. Oh, actually, did we, on page 100, did we go through this? We didn't, did we? No. Okay, so let's go through this. Yep, okay. So how does the pH at the equivalence point change as the acid becomes weaker? So down at the very bottom, we have our strong acid. Okay, there's our strong acid. And then we have progressively weaker and weaker and weaker acids, because acids, their Ka, the smaller the Ka, the weaker the acid. Yes? So what happens to the pH at the equivalence point, the weaker the acid? Tell your partner. The weaker the acid, the higher the pH at the equivalence point. What happens to the volume of OH, NaOH, needed to reach the equivalence point? Tell your partner, what happens as we go from our strong acid to our weaker, 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 weaker acids? What happens to the volume needed to reach the equivalence point? It stays the same. So the volume of NaOH needed to reach the equivalence point does not depend on the strength of the acid. Only on the moles of acid. We're on page 100. Is good? Okay. So let's take a look then at the pH at the half equivalence point. I'd like you to take notice of the fact that when the Ka of our acid is 10 to the negative 8, the pH at the half equivalence point is 8. if the Ka of the weak acid is 10 to the negative 6, the pH at the half equivalence point is Thank you. 6. And if we have a Ka of negative 4, everybody, what is the Ka at the half equivalence point? 4. Okay. So, and I think 2 is just a little weird. I'm not quite sure what the book was doing there that I stole this image from. But the thing to note is that the pH at the half equivalence point is equal to the pKa of the acid. Ooh, yes? And the reason for that is that, remember, that also means that hydrogen ion concentration at the half equivalence point is equal to what? Equal to Ka. Now let's remind ourselves, Ka is equal to H plus times A minus over HA. What's true at the half equivalence point? At the half equivalence point, the concentration of HA is equal to the concentration of A minus, which means that in this equation, Ka here, if A minus and HA are equal, what happens to them in the Ka expression? They cancel out. So the H plus at the half equivalence point is equal to Ka. Isn't that nice? Okay. Next page. Oh, look what we have here. We have a titration of a weak base with a strong acid. Where is the weak base? Is it in the flask or the burette? It's in the flask because our initial pH is high. Okay, so down in here we have our weak base. In this case, NH3. And what we're dripping into it is a strong acid. So HCl. And our equivalence point, what do you notice about the pH at the equivalence point? Is it 7 greater than 7 or less than 7? It's less than 7. And I'd like you to see if you can explain to your partner why. Why is the pH less than 7? Or actually, maybe it'd ask us down there. Does it? Okay, there we go. Yeah. Actually, why don't we just answer these questions? Because they're here and we have space to write the answers. That makes sense. What would the initial pH be if the base in the flask were 0.1 molar NaOH instead of 0.1 molar NH3? It would be 1, right? Because we have, what's 0.1? 0.1 is, or actually, no, it wouldn't be 1. That would be our pOH. So our pH would be 13, okay? Because our concentration of hydroxide is 0.1, which is 10 to the negative 1. So our pOH then is 1. And that means our pH is 13. So you can tell the difference between a strong base and a weak base, because the strong base, the pH will be dependent just on the concentration, not on the strength, because it's strong. Why is the initial pH of NH3 lower than the initial pH of NaOH solution of the same concentration?
Is a strong base.
Mm-hmm. How does NH3 make hydroxide? You have to have water in there, right? It doesn't have OH on its own, so it needs to react with water to produce NH4 plus OH minus. Write the reaction representing the neutralization of NH3 by HCl. One-way arrow or two-way arrow? One-way arrow. How do we know?
HCl.
HCl is strong, and as long as one of them is strong, it will go to completion. All right, and our products are H4 plus and Cl minus. So tell your partner what is the equivalence point and what species are present at the equivalence point. What is the equivalence point? The equivalence point is when all the reactants are used up and there's no leftover, excess. So how much NH3 and HCl are left at the equivalence point? Nothing. They're all gone. So who are the only species present? NH4 plus and Cl minus. Now, when you get to the equivalence point, you need to say to yourself, I made a better point of this in block 8 than I did with you guys. When you get to the equivalence point, you need to say, who is the salt? Who is the salt? Because the salt is the only thing that's left. And the salt is going to be what determines your pH. Okay, so at the equivalence point, what should you be looking at? The salt. At the equivalence point, who are you looking at?
Salt.
The salt. Everybody, at the equivalence point, what are you looking at?
The salt.
At the
Equivalence point.
equivalence point, what are you looking at?
The salt.
At the everybody, what are you looking at?
The salt.
There's still people in the back row who are not with us. I want everyone to turn around and look at them. Front row, your back, middle row, everyone turn around and look at people in the back row, stare at them until they start saying it with us. See, they didn't even hear that, man. Okay, at the, look at the, you guys aren't very good at like being intimidating. I have to be intimidating all on my own. Oh. Well, I have to stand up higher because I can barely see them. I'm too short. Everybody in the back row only. Oh, super fun. Back row only. At the, look at the, at the, at the, I can't even see your mouth moving, Charlene. At the, what do you look at? See, they don't know because they're not listening. You got at the equivalence point, look at the salt. At the equivalence point, look at the salt. At the equivalence point, look at the salt. Okay. All right. Who are the ions in our salt? NH4 plus and Cl minus. Do they hydrolyze? Does NH4 plus hydrolyze? Yes. Does Cl minus hydrolyze? No. Write the hydrolysis equation. Who are the products? NH3 and H3O plus. Tell your partner, is that producing an acidic or basic solution? Acidic solution. So if I say to you, why is the titration of a weak base with a strong acid, why is the pH less than 7 at the equivalence point? Because we got a salt that contains an ion that will hydrolyze to produce H3O plus. And to be honest with you, I would probably just write the reactions because that's a more powerful way of explaining it than using words. Because you can say, we make NH4Cl salt. NH4 hydrolyzes. Bam, write the equation. Oh, look, we've got the hydrogen there, so it is acidic. Excellent. Okay. Now, actually, I would like you to tell me several differences between this curve and the curve of a strong base with a strong acid. I don't know how this answer key kind of ended up in the middle of here. I need to work on that, but that's okay. Four differences between those two curves. Chat amongst yourselves, come up with 4 differences. Oh, and by the way, you can go have an apple. They're on the
Table here in the box. Ooh, and Rocha. Yeah.
What's one thing that's different about these 2 curves? The weak base curve,
It's lower.
it starts at a lower pH, right? Less basic. pH. What is another thing?
Okay.
Yeah, the weak base curve has a hill at the beginning. The strong base doesn't. So I'm focusing on the weak base. So the weak base has a hill at the, and I'm going to put it in quotes, hill at the beginning. What else is different? Yeah. Yeah, the equivalence pH is less than 7. And what's the difference in the vertical sections? Yeah. Yeah, it's got a shorter, has a shorter vertical section. Okay, and you could make those same comments if you were comparing a weak acid being titrated to a strong acid being titrated. This just happens to be weak base. What do you look at when you come to the equivalence point?
The salt.
The salt. Okay. Okay. Okay, so there were some practice exercises. You did numbers 1 and 3. How about you do number 2 right now? So this is on page 103, number 2. All right, so the pH at the equivalence point is always less than, greater than, or equal to 7 for a strong. Always equal to 7. Now, if we have a weak acid and a strong base, the pH at the equivalence point will be Greater than 7. And if we have a strong acid, weak base, the pH at the equivalence point will be less than 7. And that's because for the equal to 7, we have a neutral salt. For pH greater than 7, we have an acidic salt. And for pH less than 7, we have a basic salt. And we have to look at potential hydrolysis. Is good? Of course, the neutral salt doesn't hydrolyze, but. All right. Yes? Did I do it backwards? Yes, I did backwards. I saw a look on the face. I was like, oh dear, what have I done wrong? Okay, basic salt and acidic salt. Thank you. I got them backwards. Sorry about that. Okay. 5.6c. Choosing an indicator for an acid-base titration. This is on page 106. Oftentimes, all one word. My God, I obviously stole this from somewhere because I would not use a word like oftentimes. In an acid-base titration, an indicator is used rather than a pH meter. Optimally, an indicator should change color at the pH of the equivalence point. So if we look at this strong acid, strong base titration, who looks like they would be a really good indicator? The one in the middle would be a good indicator, yes? Because it changes from pH 6 to pH 7.6. However, when we did our strong acid, strong base titration, did we use bromthymol blue? No, we used phenolphthalein, which changes pH from 8.2 to 10.0. Why was it okay to use phenolphthalein rather than bromthymol blue? How much extra NaOH does it take to raise the pH from 7.0 to 10.0? And remember, what are we reading along the bottom? So volume of alkali added, we could rewrite that as volume of NaOH added. Not a lot. In fact, virtually none. Yes, that vertical section is just like boom, right? It whips from about pH 3 to pH 10 in maybe a half a drop. Yes, at most. So you could really use anything that changes within the vertical section. It will still give you the same volume as something that changes at exactly pH 7. Okay, so if you have a strong acid, strong base titration, anything that falls within the sort of, 4 to 10, 3 to 10 range will do just perfectly fine because it will change at the same color at the same volume. Okay, so those are 3 good choices. Are there any other choices that we could make? Let's look on our data pages. So our vertical section, and generally they're not going to make you remember a vertical section. They'll give you a picture of a vertical section, right? And the vertical section was from pH 3 to 10, approximately there. So which indicators could we not use? That might actually be a faster way of going about it. We would not want to use who? Methyl violet would be a bad choice because it changes pH way too low. We will not be anywhere near the equivalence point. We would also not want to use maybe thymol blue. Let's check and see where thymol blue's second transition point is, because if you remember, thymol blue doesn't have 1 transition point, it has 2. Could we use thymol blue? We could. Its second transition point would do us quite nicely. You might actually see 2 transitions, though. It might get you a little confused, but it would be pretty. Okay. Orange 4? No. Orange 4 will not get us there. And just likewise, we wouldn't want to use alizarin yellow or indigo carmine either. Okay? So basically, you can see here, you wouldn't want to use alizarin yellow. It might kind of maybe be okay, but you're getting to the range of where it's not. And definitely methyl violet, you're only like, what, 2/3 of the way to the equivalence point when it changes color. You'd be like, I'm done, but you're not done, right? So it would indicate before you reach the equivalence point, which is useless to you. So please define endpoint and equivalence point so that you have those 2 concepts in your head. The end point is the point in a titration where the indicator changes color. The equivalence point is the point in a titration where all the reactants are used up and there is no excess or leftover. Okay. Or you can say it is the point at which the stoichiometry of the reaction is perfectly fulfilled. I kind of like that one, but I know that lots of other people don't. So the point in the reaction where the stoichiometry of the reaction is perfectly fulfilled. Okay, the graphs below show the titration of a weak acid with a strong base. Write down, for each of the graphs, write down the volume of NaOH added to reach the equivalence point. So we want the volume of NaOH needed to reach the equivalence point and the volume of NaOH needed to reach the end point. So the equivalence point and the end point. So there's places for you to write it down below. I hope it's pretty obvious that for the first one, to reach the equivalence point, it required 50 milliliters. Was that easy? We look here and we go, where's our vertical section? It's at 50 milliliters. So that's the volume required to reach the equivalence point. The end point is where the indicator changes color. So it's midway through this color transition here. So it reaches its color transition about there. Oh, guess what? What volume does that occur at? 50 milliliters. Is this an appropriate indicator? Is phenolphthalein an appropriate indicator for a strong base weak acid titration? Yes. Now, the next one, methyl orange, changes between 4.2 and 6.0. So the halfway point there is, what, 5.1? 5.3? 5.3? 10.2 divided by 2 is 5.1. 5.1. Okay. So what's the volume of NaOH needed to reach the equivalence point for our second graph? 50. Okay, easy peasy. What volume is needed to reach the end point? 30. Somewhere in the neighborhood of 30 anyway, right? So is methyl orange a good choice? No, for a strong base weak acid. Probably it would be okay for a weak base strong acid. Yes? Oh, what it means is, do the equivalence point and the end point match up? Or is your indicator changing color before you get to the equivalence point or after you get to the equivalence point? Okay, so these should match. Good question. Okay, and we're down to the exercises, and let's just see what we've got here. Oh, there's some titration question, calculation questions here, just to remind you of them. So yeah, you could do page 108, 109, Oh, 109, 108 to 110. Yeah. And can I just let you work on that? We have a little work time this class, and tomorrow we will start our new unit, which is electrochemistry. And I'm sorry, I screwed up. I have a draft sitting in my drafts file, sending my request for printing to the printer. So we're going to get a stapled booklet because I had to make it myself. I'm so sorry. When I went to go pick up my order, I'm like, there's only half the books here. And she's like, you didn't send another order. I'm like, what? Ah! And then I found it in my drafts. I hate that. I need to start checking my drafts like regularly just to be like, what have I not sent this week that I thought I sent? And if there's anyone who was away last day and did not get the overall unit review, it is here. Okay? Overall unit review. Okay, what species affects the pH once you are past the equivalence point? Oh, that should be NaOH.
Yeah.
Or is- Oh, at the equivalence point, it should be NaA.
Oh,
Is the answer key wrong? Let's go look.
no, but yeah.
Yeah?
Yeah. It's
Oh,
like-
no. Okay. Did it say A minus?
Yeah.
Oh, NaA is the same as A minus. Na is a spectator.
Oh, got it.
Yeah?
Oh, after the equivalence.
After the equivalence point because you've added more NaOH,
Oh,
right?
oh yeah. I thought the more like salt like this like hydrolyzed.
Yeah, no, the salt just hydrolyzes and then you're like, and I'm going to dump in a whole bunch more NaOH now. And so the NaOH just kind of overpowers it and says, you little piddling amount of OH, you're not important anymore. Yeah? Yeah. I don't think we're going to have time to have a quiz on buffers and titrations, but would you like me to give you a practice quiz with an answer key that you could do? Okay, I will get on printing that out. So study as though there were a quiz on like tomorrow maybe, because I'll give it to you tomorrow. All right, so study as though there were a quiz tomorrow or Saturday, if that works better for you, and then write the quiz on Saturday, okay? Yeah. That's okay. That's okay. Oh, okay, because this is a phenolphthalein indicator, and it's simply the property of that particular indicator is that it changes color. That's just a property of phenolphthalein. Its personality, basically. Yeah, exactly. Exactly. Whereas methyl red, it changes from pH 4.2 to 6.0. So if you add an indicator it will change color when you want it to. But if you add in methyl red, it's usually going to be able to get to your yeah. Yeah. Yeah, exactly. So you're dripping in the right, sort of halfway through the transition. But we're not actually done because we haven't been verbal. Yeah. So we're going to do this in single line.
Yeah, but
How do I
Oh, a strong base added to a weak acid. So strong base NaOH.
Oh, just
Yeah. Yeah, because NaA is also a strong base. A minus is a base. Yeah. Yeah.
because this is this picture.
Yeah. Yeah. Exactly. Yeah.
Okay, no, it's awesome.
Okay, which of the following is the additive solution potassium fluoride? Oh, this is the tricky one. This is actually a star question. So, some sort of writing implement. There we go. Okay.
So ideally, you would probably be like, I'm really gonna get that first, right? So, just prior to start a little bit more, what if I put potassium instead of S? What if I just put F minus with OH, what and kind of react? What if I put potassium? What if I put it with hydrochloric acid? Only react after this. So it's like the. Oh, because you're putting half the number of moles. Yeah. Yeah. So it's like the buffer zone in the titration, right? When you're halfway there, you're right in the middle of the buffer zone. Yeah. You're welcome.